Okay, so our next result is this one, lemma 4 to 4. So here we are given a vector space V over some field F, and a basis of V is given consisting of these Vi's, n number of vectors in V, which form a basis for V over F. Additionally, some m vectors are given. Among these m vectors, we may or may not have these Vi's. Okay, that's not the point. There are some m vectors in V, and it is given that they are linearly independent. Then we have to prove that m is less than or equal to n. That is what this lemma says, is that if you have a vector space in which n vectors form a basis, then there can be at most n linearly independent vectors in the space that one can possibly find, not more than n. In particular, for example, in this vector space V, you cannot find n plus 1 linearly independent vectors. That is not possible by this lemma. So let us see the proof. Since every vector in V is a linear combination of the basis vectors in particular, this Wm also is a linear combination. And our conclusion is this. Thus, if we include Wm among the Vi's, then the resulting set will be linearly dependent. Why? The reason is simple. We are saying that Wm is some linear combination of the Vi's. So that means there are some scalars alpha i's coming from the field such that Wm looks like this. And this implies we have an equation like this: alpha 1 V1 plus alpha 2 V2 and so on, alpha n Vn equals 0. That means a linear combination of these vectors, the Vi's along with Wm, is 0. And this is a non-trivial linear combination because all the coefficients are not 0. In particular, this coefficient, which is -1, is a non-zero element in the field. It's a non-zero scalar. So this equation tells us that these vectors are linearly dependent. Okay. Also, they span V, since the basis vectors already do so. The basis vectors have two properties that define a basis. They span the whole space and they are linearly independent. So because they are spanning the whole space already, so an introduction of an extra vector will not change the span. This superset will also span the whole space. Thus, by the first corollary to theorem 421 there exists a basis of V of the form this, where k is less than or equal to n minus 1. What have we done here? Let us see. We have applied the first corollary to theorem 421. So theorem 421, if you recall, is a result that says that if we are given a number of vectors in a vector space, say a list of vectors v1, v2 up to say vn, then either those vectors are linearly independent or some vector among them is a linear combination of the preceding ones. This is something we have already seen, and it has a corollary which is very important. The corollary looks like this. The corollary says this. We are given some vectors in a vector space V, and W is their linear span. Additionally, it's given that the first few of them are linearly independent. Then there exists a set of vectors which looks like this. IR that also spans W and that consists of linearly independent vectors. In other words, there exists a subset of this set of vectors in V which looks like this and which forms a basis for W. When we stated corollary 1, at that time the definition of a basis was not, the notion of a basis was not available to us. But this can of course be restated like this. If these things are true, then W has a basis of this form. Okay, that's what we are using here. But how exactly are we using here? What is our this set in this case? In this case, this set is this. In place of the V's we see here, we have this. Okay. Now, this is a set in V which spans W. For us, in this case, W is V. Okay, because these vectors span the whole space. And what is these first few vectors in our case? That is this single vector. So that means we will be able to find a basis of W of this form. In our case, a basis of the entire space V of this form, where in this part we have only Wn and some other extra vectors from the original set. Those extra vectors are these, and we are saying something else also. Among these extra, there are k extra vectors where k can be at most n minus 1. Now why is that so? That is because this set is linearly dependent, so the entire set cannot form a basis because it's not linearly independent. For linear independence, some vectors have to be removed from among these. The application of corollary 1 fixes this Wm part. These vectors are fixed, they are unchanged. They stay here from the beginning and they don't change when we make the conclusion. Just like that, here Wm is unchanged. The rest are changing and we can only remove vectors from the V's. And we have to remove because these are linearly dependent. Only after some removal we get a linearly independent set. How many of them we have to remove, we don't know. After removal, k of them will be left. But we can say that this k has to be less than or equal to n minus 1. It cannot be equal to n. One more thing that must be seen here, that must be justified, is we are saying in place of this fixed k vectors, we are taking the single Wm. Is this set linearly independent? If not, then we cannot possibly make this conclusion, and by applying corollary 1. It is linearly independent. Now, when is a single vector linearly independent, or rather I should say like this, when is a set consisting of a single vector linearly independent? Namely, precisely when the vector is a non-zero vector. Is that the case? Yes, because the Wm is itself coming from a set of vectors which are given to be linearly independent. That linear independence demands, among other things, that all the w's should be non-zero. If you have the zero vector in a set, the set is linearly dependent. This is also something we have already seen. So that's why we are able to apply this corollary and make a conclusion like this. Okay, so that means, so do you see what we have done? We started with a basis. We have now obtained another basis in which we have introduced one w from among these w's, and we have lost at least one v, possibly more. We have our loss will be exactly 1 v if k becomes equal to n minus 1. Otherwise, we have lost more v's. Let's just keep this part. Now we are going to move forward from this conclusion. So this is our basis. This is a new basis. Now if we repeat this procedure, what can we then say? We have to also say exactly in what sense are we going to repeat this procedure. Repeating this procedure means now we will start with this new basis, but then what? We will introduce another w and see what happens. But before that, here in Herstein's exact words, we have traded off one w in forming this new basis for at least one v at the expense of at least one v. one more remark, a notational remark. We have obtained this basis by removing some v's. Since we don't know exactly which vi's are being removed, so we don't know what we will be left with ultimately. So we have some suffixes I1, I2, which of course you can clearly understand are from among the n suffixes 1, 2, 3 up to n. Okay, now if we repeat this procedure, repeat this procedure with, or I think we should write repeating this procedure with the vectors Wm minus 1, Wm, Vi1, etc., Vik. We can extract a new basis with the vectors which are linearly dependent. Actually, there are two lines. Let me write those things in one line itself, which are linearly dependent. All the justifications are also going to be repeated. Just like we introduced Wm among the Vi's, we got a linearly dependent set. Now introducing Wm minus 1 among these basis vectors, again we are going to get a linearly dependent set, which are linearly dependent. We have again by corollary 1 to theorem 4 to 1, a basis of V of the form Wm minus 1 Wm. Now we are removing the v's that are available here. So some new suffixes j1, j, s, where s now has to be less than or equal to n minus 2. And you can understand, just like before, here we are again using corollary 1, but exactly in what way? Now this part of fixed vectors, for that part we choose these two vectors Wm minus 1 and Wm, so they remain. From the rest of the vectors we are removing, so these j's are from among the i's, I1, I2 up to Ik, some of them. But since again this set is linearly dependent and we are removing to form a basis which among other things is linearly independent, so something will be removed from these vi's, the other suffix. So s cannot be equal to k, and in the best possible scenario where k is n minus 1, s cannot be equal to n minus 1. S is never equal to n minus 1. S must be less than n minus 1. It can at most be n minus 2, which will happen when this happens. K is n minus 1, that means from the original set, this set, we have had to remove only one vector. So this k is n minus 1. Which one we don't know, but some one vector. And then in forming this new basis, from this new linearly dependent set, we have to again remove exactly one vector, then s will be n minus 2. That's the highest value s can have. Okay. Keeping up this procedure, we will eventually reach a situation like this. We will eventually get down to a basis of the form W2, W3 up to Wm minus 1 Wm and possibly some V's. And to get to this basis, we had to introduce m minus 1 W's, but before that something else has to be said. The fact that in this basis that we have, the latest basis, there are actually some V's. Since W1 is not a linear combination of the other W's, this basis, this latest one, must actually contain some V, some V's. What we are saying is that W1 is not a linear combination of the other W's. Why? Because if that happens, then the W's will form a linearly dependent set, but it is given that they are independent. So W1 cannot possibly be spanned or be generated by the new basis if that does not contain any V's at all. If in forming this final basis, final I am saying final form now, okay, if in forming this final basis we have run out of the V's, we have in fact managed to remove all the V's. If that happens, then there is a problem, because then W1 will not belong to their linear span. Okay, so it cannot possibly be a basis. So at least one v must have survived in this process of removal. Okay, to get to this basis, we have to introduce m minus 1 w's. M minus 1 w's, w2, w3 up to wn. Each such introduction having cost us at least one v. And still there are v's left. At least one v for each introduction of w, because the moment we introduce a new w to the existing basis, latest basis at that stage, we get a linearly dependent set. And we want to keep all those w's that we have introduced so far. So that forces us to remove some v, at least one v, but so that's what we are saying, that each such introduction having cost us at least one v, possibly more. And still, after introducing m minus 1 w's and losing at least m minus 1 v's, still v's are left in this final basis. Thus, m minus 1 should be less than or equal to n minus 1, because if this is not the case, then we would have run out of the v's. And so m is less than or equal to n, and that's how we obtain this final conclusion. But there is still one gap. You may ask me, what happens if we don't reach this stage at all? Then what happens? Like we don't get to reach W2. Before that itself, we run out of v's. So that if you then introduce a W, you have to remove w's, because there is no v and you are getting a linearly dependent set. To make that linearly independent, you have to remove some w. What happens then? That stage will be never reached because of a similar reason that we said just now. If we run out of the v's in the middle somewhere, then the procedure says that every time we are ending up with a new basis. So that means we have again got a basis consisting of some of the w's, but not all the w's. Okay. But then the remaining w's that we have, they are not among these w's that are forming the basis. So how can they be generated by this w? So in essence, those w's cannot form a basis. So not only in this, at this stage, but at any stage, in getting to this stage, we will never run out of the v's. Always some v will be left. So we will be able to get to this stage, and then again using that same logic, we come to the conclusion that some v's are left, and that's why we are getting this. So this completes the proof. And this result will now allow us to define the dimension of a vector space, of a finite dimensional vector space. Looking at the statement of this lemma, one immediately sees that a direct consequence of this lemma is that any two bases in a finite dimensional vector space must have the same number of elements, and that is the first corollary to this lemma. This lemma has as consequence, these are some lines written by the author. This lemma has consequences which we list as corollaries, the basic results spelling out the nature of the dimension of a vector space. These corollaries are of utmost importance in all that follows, not only in this chapter but in the rest of the book, and in fact in all of mathematics. The corollaries are all theorems in their own rights. This line, it can be overlooked easily. These corollaries are of utmost importance in all that follows, not only in this chapter but in the rest of the book, in fact in all of mathematics. It seems like the author is exaggerating the importance of vector spaces and linear algebra in general, but this is not an exaggeration. Wherever you go in mathematics, you will in one form or another encounter linear algebra. The reason is this: you are studying something where you get equations and some relations. Either those relations are linear or they are non-linear. Okay. Linear mathematics is naturally easy because of its linearity and simplicity. Non-linear equations, whether they are algebraic equations, polynomial equations or differential equations, they are inherently complicated, and in most of the cases they are so complicated that one cannot work with them analytically as such. They have to be simplified, and such simplifications involve linearizing those things. So you end up in linear algebra again. So there is it's somewhat of a joke. Anything in mathematics is either linear algebra or linear algebra. That's the thing. Okay, so what the author is saying here is not an exaggeration at all. In fact, these ideas are important in all of mathematics. So let us see the corollary. If V is finite dimensional over F, then any two bases of V have the same number of elements. Have the same number of elements. So let us see the proof. So because V is finite dimensional, it will have a finite basis. Recall that finite dimensionality, according to how it has been defined in this book, is by definition not having finite basis. The definition of finite dimensionality in this book demands or says that a vector space is finite dimensional if a finite subset spans the space. Then we saw through our analysis that ultimately comes down to having a finite basis. Okay, so we can start with having a finite basis. So that means there are two bases or finite bases are there. Okay, so we will now take two finite bases and show that they have the same number of elements using this lemma. Let v1 vn and p2 bases of v over f, and we are continuing to write these vectors without using the precise set notation. We are saying that this is a set of vectors which forms a basis. Ideally we should write like this. This is a set, this is not a set, this is just a list of vectors. But such distinctions don't change the thing. I mean, we are being somewhat non-rigorous here. Still you can understand the things. We are not making any mistakes, any serious mistakes by not using curly brackets. That's what I am saying. So these are two bases of v over f. Since this is a basis and the w's are linearly independent, they are linearly independent because they also form a basis, and being a basis they are linearly independent. It follows from lemma 422 that this is m is less than or equal to n. The number of linearly independent vectors cannot exceed the number of elements in a basis. But we can do this thing with the roles swapped. We can consider this as a basis and these vectors as linearly independent. Doing that, we will get the opposite inequality. Interchanging the roles of the v's and the w's we get n less than or equal to n. So n must be equal to n, and hence any two bases of v over f have the same number of elements. That number is fixed, but note that the bases themselves are not fixed. A single vector space of say dimension 2 can have many bases but each such basis will have exactly 2 elements. That number is fixed, and this leads to the definition of dimension. But before that, there is this corollary 2. The space of n tuples over if n is isomorphic to fm, if and only if n is equal to m. This is something we suspected in the previous video. We in fact had a heuristic discussion also about this, but now we can say with certainty that whatever we felt should be true there back then is actually true. So if n has a basis consisting of these n vectors, all of these are n tuples, each having n components. That is understood. It's very easy to see that these vectors span Fn and they are linearly independent, which I think we have already done. Similarly, if M has a basis consisting of m number of vectors, a similar basis. Now, existence of an isomorphism between Fn and Fm demands that such two bases must have the same number of elements, and that in fact we haven't proved yet, but that is one of the exercises. So we are going to write like this: an isomorphism between Fn and Fm the exact language is this: an isomorphism, this because of this fact maps a basis onto a basis. See exercise 4 at the end of this section. So n is equal to m if fn and fm are isomorphic. The converse, of course, is obvious. If n is equal to m, then automatically fn and fm are isomorphic. In fact, they are the same thing. Okay, so we don't even bother mentioning the converse. So this is corollary 2. So after that, the author is saying corollary 2 puts on a firm footing the heuristic remarks made earlier about the possible isomorphism between fn and fm. As we saw in those remarks, v is isomorphic to fn for some n. That also we saw. No? In those heuristic remarks, we considered a finite dimensional vector space V. In fact, that's where the discussion started. Being finite dimensional, that vector space had a finite basis consisting of some n vectors. What we then did, we defined a map like this, where any vector in V, which is of course a linear combination of the VI's, were mapped onto this n tuple. Okay, and we showed, or I think mentioned, it's in fact quite easy to show that this f is an isomorphism of v onto fn. So v and fn are isomorphic, and then we said that there is the possibility that v and fm are isomorphic. Maybe v has another basis consisting of m elements, and then that question arose, under what conditions are fn and fm isomorphic. So now we know that they are isomorphic precisely when n is equal to m. And this okay, let me at least write this part. As we saw, in the previous heuristic remarks, that V is isomorphic to Fn for some n. Now by this corollary 2, this n is unique. And this n is defined to be the dimension of V. Oh, and okay, so we can rephrase things. I mean, we can summarize this whole thing as a third corollary. Corollary 3. I need some ink, a little ink. If V is finite dimensional over F, then V is isomorphic to Fn for a unique n. In fact, n is the number of elements in any basis of V. Yeah, now we can say that this number is defined to be the dimension. The integer n in corollary 3 is called the dimension of V over F. Okay. The dimension of V over F is thus the number of elements in any basis of V over F. Yes. We have already said that here. Now, we shall write now the notation for this quantity as dim V or in the occasional time in which the mentioning the field will be important, we shall want to stress the role of the field F. It will be denoted as dim suffix F V, and we will read this symbol as dimension of V over F. After this, there are some results which say what sort of freedom we have in choosing a basis for a finite dimensional vector space. Now we know that that number is fixed for a given FD vector space, finite dimensional vector space, which is its dimension. But fine, then What about our freedom of choosing a basis? How can we choose bases and what type of bases are there? In particular, we can, by now we already know there are many bases for a given vector space. Do they have anything in common? How they can be chosen? That is one thing. And we will also calculate the dimension of this quotient space. Say V is a vector space and W is a subspace. We already know we can form the quotient space V by W, whose elements are the cosets of W in V. Cosets as the in the cosets of W as a subgroup of V under vector addition. Okay, so we will show that if V is finite dimensional, then W is also finite dimensional and V by W is also finite dimensional, and in fact the dimension of V by W is the dimension of V minus the dimension of W. With this result, I think the section will end and then there are exercises. So that will be all in this video for tonight. You can comment in the comment section below if you want to say something about these things or about anything else mathematical. Tomorrow we have again Galilean's exercises, both groups and rings. Tomorrow we have Galilean's exercise, okay, and then day after tomorrow analysis. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.